Um, Today we'll discuss in this video 2023 October paper, Unit 1. So let's start with the first question. So first they are asking uh, a quantity is either a scalar or a vector. Which row of the table is correct? Like we should find what are scalars and what are vectors. So a scalar is a physical quantity which does not have a direction. Okay, so here if you take possible options are energy, time. These two have direction, so they cannot be considered as scalars. Vectors are quantities which have a direction associated with it, so we cannot take mass here. So it's momentum. Therefore, we can get the answer as A. And another important thing to note is if you take momentum, so momentum is equal to mass into velocity. Mass is a scalar and velocity is a vector. So when you multiply a scalar by a vector, you get a vector itself. And it's better if you remember, if you multiply a scalar by a scalar, you still get a scalar quantity. But if you multiply a vector by a vector, generally, right, not always, generally you get a scalar quantity again. Right? One example is if you multiply, uh, like to get work done, what we do is we multiply force into distance, right? Actually, this is force. This is the distance in the direction of the force, in the direction of F. Therefore, if you think it deeply, both of these are vectors because distance is a scalar, but if you take the distance in a certain specific direction, it is a vector. Therefore, here we multiply a vector by a vector, which will result in a scale. Okay, so simply if you multiply scalar by scalar, it is scalar. If you multiply vector by vector, it is scalar. If you multiply scalar by vector, it is vector. Generally, this is the idea, but sometimes there are exceptions. But just note this down. It might be an important point sometimes. Okay. What is the SI unit for momentum? Next question. So it is easy, right? Momentum is mass into velocity simply. It is this one. kgms minus 1. It's an easy question. Third one. Which of the following could be used to describe the elastic limit of a material? So if you take a material, there are some important points in this stress strain curve that you should know. Let's say it is like this. Okay. So there's one limit called proportional limit, and there's another limit called elastic limit. Let's talk about these two. Right. So proportional limit, as you all know, point at which material won't obey Hooke's law, right? Okay. Simply, what happens is if you stretch a material above the proportional limit, the force won't be directly proportional to the extension. But if it is beyond, like if it is before the proportional limit, the force will be directly proportional to the extension. That is a simple point that we all know. And elastic limit undergo deformation. Above the elastic limit, the particle will undergo deformation. So, what is this deformation? Deformation means something like this. If the original length of a string is 10 centimeters and if you stretch it up to 14 centimeters and if you release it, suppose you stretch it and suppose you release it. So when it is released and if it has passed this elastic limit, then it won't come back to 10 centimeters. It will come to something like 10.5. Right? This is called deformation. Like it won't return to its original length when we stretch it and when we extend it and release it. Right? That is called elastic limit. Okay, but proportional limit is not that. Okay, so if you are between the proportional limit and the elastic limit, suppose you are between in this region. If you are in this region, the material won't obey Hooke's law, but still it will come to the original length. Still returns to original length. So that's the point. Okay, I hope you understand. Right? Above the proportional limit, it won't obey Hooke's law, but still it will come to its original length. But if you have passed the elastic limit, obviously it will not obey Hooke's law, and also it won't come to its original length. So the answer should be this one, right? Material will be deformed. That's how it. Okay, right. Mm. Fourth question. Like if you have any unclear points, you can put a comment. Okay, I'll respond. Fourth question: a ball falls through air from rest. A ball falls through air from rest. Which of the following uh, which of the following graphs show the displacement against time? So first of all, by looking at this question, you can see the displacement is negative, right? So first of all, you should identify the direction. So this says that ball falling downward, or simply the downward direction, is considered to be negative. Right? Downward direction is considered to be negative in this situation. How did I think about it? By looking at the options given, right? In all the options, they have given the graph towards the negative side. That means we should consider downward to be negative. Downward direction to be negative. Okay. So if a ball is falling from air through rest, one data we can take is it's falling under constant acceleration. Under gravity. Okay. One thing is it's falling under constant acceleration. Okay. So if you take the velocity time graph of that situation, what happens? If you draw the velocity time graph, it should be something like this, falling under constant acceleration, and it is in the negative direction. Now we should map the displacement time graph by looking at this velocity time graph. One strong tip that I recommend you to do is just write what happens to the velocity here. Now I can write velocity increase, or we can say negative velocity increases, right? You can say here negative velocity increases. Okay, this is what I have written for the velocity time graph. Then if you want to convert this velocity time graph into a displacement time graph, what can you do? You can cut this and put the word gradient there. So it means the negative gradient increases. So negative gradient increases in this option, right? See. So that is the answer. Okay. Negative gradient increases. That's the whole point. Right. Then question 5. A helicopter moves vertically upwards with an increase in speed. Which of the following describes the increase in gravitational potential energy? The helicopter. Okay. So we have an equation saying work done is equal to change in energy. Okay. So here surely it should be something related to work done. Okay. It should be something related to work done. But they are asking which of the following describes increase in gravitational potential energy. So here we should add another word, change in gravitational potential energy. So simply if you take the equation work done is equal to change in, that's the general equation, right? But if you take this situation, they have told about specifically told about gravitational potential energy. So change in gravitational potential energy is work done associated with gravity, right? Should be surely associated with gravity. Okay. So by looking at that, we can say total work done, that is wrong. Because for the total work done, there might be many factors affected, like there might be a wind resistance, so you should do work against it as well. Likewise, I mean there are many factors. But here we should consider work done associated with gravity. Work done by the helicopter to increase speed, that is also wrong because it is not associated with gravity. Now we have two options which say work done by the force of gravity and work done against the force of gravity. So we should select one option out of these two. So work done associated with gravity, and helicopter is moving upward. Gravity is acting downward, right? So surely work is done against the force of gravity, right? If the helicopter is moving upwards, the work is obviously done against gravity, right? But if the helicopter is moving downwards, the work is done by the force of gravity. So we like broke down this question into two parts. First of all, we analyzed like the basic equation, and we found that it is associated with gravity, and then we analyzed the direction, like to which direction should it act. Okay, next question. An object moves with a velocity v, kinetic energy is doubled. Then they are asking about a new expression, so we can say kinetic energy is doubled, so E is equal to half m v1 squared for the initial situation, and for the second situation we can say this v2 squared. We can take them as two equations and then divide 2 by 1. So if you can divide the left side first of all, and then you can divide the right side then. Okay, so we can cut this half m half m, then we get 2 is equal to v2 squared over v1 squared. This says v2 squared is equal to 2 v1 squared. So v2 is equal to root 2 v1. Okay. So v1 means this velocity which we considered. Okay. So the answer should be A. I think it's clear. This one. Okay. Right. A power station produces an electrical output power of 2.1 gigawatts. The power station transfers thermal energy to the surroundings at a rate of 3.4. So this is also obvious. They are asking the efficiency. So simply efficiency means output over useful output over total input. So it should be 2.1 gigawatts over 2.1 plus 3.4 gigawatts. So since the unit at the numerator and denominator is same, you can cut them. Therefore, the answer will be this. Okay. Yeah. Um, right. Then eighth question. A student applied a tensile force to a metal wire of length x and diameter d. Length x and diameter d. Length of the wire increased by delta x. And there's another second wire. Length of the second wire increased by 2 delta x. Okay. So they are asking what will be the length of the second wire and the diameter of the second wire. So we can put the length of the second wire to be, let's say, x dash, and diameter of the second wire to be d dash. Okay. Then we can apply the Young's modulus equation, right? So we know Young's modulus is equal to stress divided by strain. Since the first wire and the second wire both are made of the same material, we can ensure that both of them have the same Young's modulus, right? But the thing is, the first wire, when it increases by delta x, the second wire increases by 2 times delta x when the same force is applied. Same force. Okay, so here we can say, like for both the wires, we can say force divided by area over x extension divided by initial length equals. This is our original wire. Okay. Original wire. In the new wire, also they have applied the same force. Let's say the area is a dash, extension, let's say it is x dash, and it's the same length as well. Okay. So therefore we can build on this equation, right? So we can say f l naught divided by ax is equal to f l naught divided by x dash a dash. So here you can cancel. uh, yeah. This can be cancelled. Mm, yeah. So here, like if you take the initial wire, we can say this is 1 over area is what, pi times PO2 squared into x equals 1 over, let's suppose the new wire's diameter is d dash. Okay, the area, and the extension is x dash. Then we can cut, yeah, we can say uh, 1 over d dash squared x dash over 4. So here I can cut this 4 and 4. So I get mm, so wait a minute. So yeah, I have done a small mistake, right? So here, actually in the second wire, the length is 2 times delta x. Okay, so that is a mistake I have done. So let's correct that. Okay, uh, we can do it like this. In the first wire, the extension was delta x, right? The initial length is x, and they are also asking about the initial length. I thought they are asking about the extension, so that's a small mistake. So we can say f over a divided by x over L naught equals, here it is delta x, okay, delta x over x equals f over a dash divided by 2 delta x over x dash, because this is our available wire and this is the new wire, right, original wire, and this is the new wire, right. Let's see that. So we get fx divided by a times delta x equals fx dash divided by 2 a times delta x, 2 a dash, okay, because in the new wire we don't know the area still. So we can cut this, and we can cut this and cut this. Sorry, we can cut delta x. Right. So we get an equation saying, uh, in the new wire, x dash over a dash ratio should be equal to 2 times x over a. Okay. So we get an equation x dash. So in the new wire, what is the area? D dash by 2 squared equals, in the old wire, what is the area? D squared by 4, right? If you take d over 2 whole thing squared, it is d squared by 4. So this divide by 4 part will get cancelled now. If you simplify this, also we get d dash squared over 4 equals 2x times pi d squared over 4. Okay. So here we can cancel this. So finally you get x dash over d dash squared should be 2x over d squared. Right. So the thing is, in the new wire, you can take the value x dash over d dash squared. It should be equal to 2 times x over d squared. Right. So let's see this one. If you take this one, uh, x dash over d dash squared value, what is it? 0.5x divided by 0.25 d squared, right? So here we get 2x over d squared. So that is the correct answer, right? Simply what we did is we compared the two wires and we identified that the uncertainty is same in both the wires. And then what we did was we just simply took a ratio of x dash over d dash squared in terms of the parameters of the original wire. Right? You should understand that. And if you take like for something like this, what is the ratio x dash over d dash squared? That is equal to 0.5x divided by 4d squared, right? 4d squared. Therefore, it is 1x over d squared, or 8d squared. So that is wrong. Okay, this is wrong. So likewise, these all should be wrong, and this should be the correct answer. Because only that answer we find that the ratio is equal to 2x over d squared. Okay, initially I did a small mistake, so just catch up with that. The ninth question, box of 8w. Yeah, this is a simple question because, like, if you consider this point in equilibrium, then surely the vectors should add up to 0. That's it. Vectors should add up to 0. That's it. Right? No other answer. 10th question. A box is pulled along the ground by a rope inclined at 40 degrees. Okay, so here they are asking the work done. So to get work done, there are two equations. One equation is force into distance in the direction of force. The other equation is force in the direction of distance multiplied by distance. I think you understood it, right? We should take one, like, simply what should happen is both the quantities should be in the same direction. That's it, right? So here we can apply this equation, right? I mean, we can take the component of the force which is in the direction of distance. So we can say here work done is equal to 30 cos 40 into 5. So you can calculate this and you will get the answer as this. Yeah, it will be 115. Okay, right. So if you have any doubt in this MCQ discussion, you can drop a message. You can put a comment. Okay. Okay. So let's go to the second part of the video. Uh, part of the paper actually. So uh, let's go to the section B, and we'll discuss. There are questions up to question number 17, I think. Yeah, there are 17 questions. We will discuss all of them now. Actually, there are 18 questions. Yeah, there are 18 questions, and we'll discuss them. Right. First of all, let's go to the 11th question. Um, Photograph shows a rocket. The rocket is launched vertically. The rocket's engines give a total upward thrust of 7.3 into 10 to the power 7 newtons. Calculate the initial acceleration of the rocket. So, how to calculate the initial acceleration of the rocket? So, we can write, first of all, we should calculate the weight. W equals mg. So, W is equal to 5.0 into 1.81. That is equal to 4.91 to 10 to the power 7 newtons. Okay. So, that is the value. So we found the weight, and then to get the acceleration, what we can do is we can apply this in the equation F equals ma, right? So 4.91 into 10 to the power 7 is equal to 5 into 10 to the power 6 into a. So we get the value for a as wait a minute. Oh, sorry. There's an upward thrust. Okay, so we have calculated the weight. So now what we should do is we should apply the equation upwards. Now let's say this is a rocket. So there is this thrust force and there is this weight. And if we apply F equals ma upward, what should happen? We should apply it like we should get the resultant force which is acting upwards. Okay, we should get the resultant force which is acting upward. If we apply F equals ma upwards, what we can do is it is 7.3 into 10 to the power 7 minus 4.91 into 10 to the power 7 equals m is 5 into 10 to the power 6 into a. Okay, right. So then a will be if you calculate, it will be coming as 2.39 into 10 to the power 7 divided by 5 into 10 to the power 6. So that is equal to 4.8 and is minus 2. So that will be the answer. Okay. So that is the final answer. So I think that's okay. And the most important thing is if you want to score the full marks for this question, you should definitely mention these equations and the proper calculations. Okay. Obviously, you get 1 mark for the final answer, but you get more marks mainly for the methods and the usage of the exact equations. Okay. Right. So the initial acceleration should be 4.8 ms minus 2. Okay. Give one reason why the acceleration will increase as the rocket rises. Yeah. So that is something you should answer using common sense. Now, what happens is when this rocket is going up, what happens? It will burn its fuel, right? It will burn its fuel. And when the fuel is burned, what happens? The mass of the rocket will decrease, and then it will increase the acceleration, right? You can say uh, due to the burning of fuel, mass decreases. Therefore, resultant upward force increases, right? Resultant upward force increases. Therefore, acceleration increase increases. Okay, this is what you should write. So here I'll write the answer as 4.8 minus 2. Okay, let's go to the 12th question. A teacher demonstrated the principle of conservation of linear momentum using two gliders, A and B, and an air track. A has the same mass as B. A and B were initially stationary. Then A was pushed gently towards B. Okay. Right now, the teacher is trying to explain the principle of conservation of linear momentum. Okay. So in the question, they are first asking, explain what is principle of linear momentum. So you should say um, when no resultant force acts on a system. Okay. When no resultant force acts on a system, acts on a certain system, resultant force linear momentum remains constant. Okay, so you'll get 1 mark for this, no resultant force on system, and 1 mark for this. So the important thing is, now let's suppose, for example, like to understand what actually this conservation of linear momentum is, let's consider a simple example. So you can take the collision of two balls. Let's say one ball is coming from this way, the other ball is coming from this way, and they are colliding. And whilst they are colliding, like there will be a force acting. This is the force acting on ball one. This is the force acting on ball two. And then after that, again they will keep moving in different directions, right? So the important point is, if you consider the system as a whole, hmm, so as a complete system, then you can identify that F1 and F2 are impact forces. So impact forces will be equal to each other. So when you consider this system as a whole, you can see throughout the situation, there will be no resultant force, right? There are forces. That's what you should not get confused is. There are forces acting in it, but there is no resultant force acting in it, right? No resultant force. Okay, right. Then we have B part. A magnet was attached to each glider. The gliders collided and stuck together. Okay. A data log and sensor we used to record the velocity of A. The velocity recorded after the collision was half the velocity recorded before the collision. Okay, so if you take A, suppose it initially went by a velocity of V, and then after striking this, its velocity had reduced to V by 2. Simply that is the story. Deduce whether these results show that the law of conservation of linear momentum is obeyed. Okay, so the thing is this now. So it is mentioned that A has the same mass as B. Okay, so suppose it is going with the velocity v and colliding and striking together. Okay, we can say there is this glider A which moves with velocity v. It has a mass of m, and there is this glider B, okay, which is stationary. It also has a mass of m. Then there is a collision. Okay, collision. There's a collision, and after this collision, what is the scenario? What is the context? There is this A and there is this B. Their masses are 2m, and they will move with a certain velocity v by 2. This is the situation, right? So if you consider the initial momentum, okay, initial momentum, it is equal to mv, because this one has no velocity, right? It is mv plus 0. From this component we get 0. From here we get mv. That is equal to mv. Final momentum, that is equal to 2m times v by 2. So it is also mv. Therefore we can say momentum is conserved. So we can say initial momentum equals final momentum. Okay. Because the mass has doubled, you should say why it is equal, right? If you want, it's better if you can draw, like if you can show this working in the space, but since there's no enough space to show that working, we can write because the mass has doubled and velocity has halved. Okay, see, initial momentum equals final momentum because the mass has doubled and the velocity has halved. Therefore, law of conservation of linear momentum is obeyed. That's it. Right. Second part. B. Second part. Explain why the force of attraction between the two magnets did not affect the demonstration. So that is an important question. Uh, that's what I told initially in this collision, right? When two balls collide with each other, there is a reaction force. Like there is an action reaction pair acting on both the balls, and since this is an action reaction pair, they are equal in magnitude. Okay, so even when the glider A and glider B is colliding together, there is a force acting on both of them, which is an action reaction pair, and both of them are equal. Therefore, there will be no resultant force. Okay, we can say um, when gliders collide. Okay, an action reaction pair it's an action reaction. So, yeah. Therefore, the resultant force on the system will still be conserved, right? System will still be conserved. So that is the situation. That's what I told before explaining this result. Okay, so here you have 6 marks. So these marks are gettable, right? So like what you should do is you should do as much as questions and then try to find patterns, especially. Right? That is also one part of learning. Okay, then let's go to the 13th question. Tennis players can practice using a tennis ball machine. The machine projects tennis balls horizontally at a height of 2.54 meters. Show that the time taken for a ball to reach the ground. Okay, so if you are going to get the time taken to be this, we know when it is thrown horizontally, there is no initial vertical velocity. Okay, so we should first formulate like what quantities we have and what we should find. Okay, so we have SUEAT. We don't know S, but we know U. Sorry, we know S, right? I mean, it's given as 2.54 meters. We know this. We know U. We should find the time. We know the acceleration, it is equal to 9.81. And we don't know the final velocity. Okay. So we should, like, first of all, we should list down this SUVAT physical quantities and then find which is missing. So in this scenario, what we don't have is final velocity. Okay, then we should try to think of an equation which contains only this four. That is equal to S equals ut plus half at squared. Okay, so for this question, you might not need to think this much deep, but for complex questions, this thinking is very important. Okay, so we can apply S is equal to ut plus half at squared downwards. U is 0 to t squared. Okay, so you get t is equal to t squared is equal to 2.54 into 2 divided by 9.81 and t will be 0.72 seconds. I think it is clear. The ball lands on the ground at a horizontal distance 17.89. So this distance will be 17.89 meters from the machine. Calculate the velocity of the ball as it is projected from the machine. So now we don't know the initial velocity. Let's say this is ux because it is a horizontal velocity, but we can calculate it simply by using distance is equal to speed into time. So ux, what is the distance it moved? 17.89. And it has fallen within zero point 0.7 second. Therefore, for it to travel from this point to this point also, it should have taken zero point 0.7 second. Therefore, we can say ux is equal to, if we divide 17.89 by zero point 0.7, we get a value of 25. Okay. So, but rather than using distance equals speed into time, it's better if you can write this way. Okay, this equals ut plus half at squared this way. And what happens is this acceleration is zero. Acceleration is zero, therefore this part will be cancelled. This is the best option, right? Like you can just write s equals ut, but it's better if you can write the full equation s equals ut plus half at squared and then put acceleration zero and then proceed. That's the best way. I think these two are easy questions. Then we have the initial velocity of the ball as it is projected from the machine can be increased. Explain how increasing the velocity would affect the angle at which the ball hits the ground. Okay, so that is a very good question. Now, if we consider like the ball is like this, okay, so we know definitely this uy initial horizontal velocity is y is zero, right? So we can say initial vertical velocity, or simply uy equals 0, right? Like even if we increase the initial velocity, that is increased in this direction, right? Because we are projecting the ball horizontally, only we can increase ux. Initial vertical velocity is 0. And also we know v squared equals u squared plus 2s downwards. It's equal to 2. V squared equals u squared plus 2s downwards. So if u is 0, okay, so we are sure that definitely this a won't change and this height won't change. Therefore, we can say final vertical velocity, what is it? Vy will be same. Okay, final vertical velocity will be same. Now, suppose the ball is landing at this point, then its Vy won't change, right? Vy will not change. That's for sure. But if you take horizontally, right? If you apply horizontally, s equals ut plus half at squared. Since a is 0 horizontally, we get s is equal to u xt. Right? Sorry, it's not that. We can say, yeah, horizontally we can say v is equal to u plus at. V is equal to u x simply. Right? Then we can say if initial velocity increases, right? Final vertical horizontal velocity increases. Final horizontal velocity also increases, right? Final horizontal velocity also surely increases. Okay. So what will happen? Now this in this direction you will have a longer line. Initially it will be something like this. Now, final situation it will be something like this. Okay. So what will happen to the angle? Hmm? We can say vertical component won't change, but the horizontal component will change. Okay. So if you take initially if the angle is this thing, now when this horizontal component increases, like say if it is something like this, the angle will be something like this. But if it is something like this, what will be? What will happen to the angle? It will bend towards the horizontal, right? This way. Okay. So what will happen? Angle with horizontal will decrease. You can understand the whole story using these diagrams. Okay. Yeah. You can just it's better if since there are 3 marks, you will get 1 mark for this, 1 mark for this, like 1 mark for stating that final vertical velocity won't change, 1 mark for stating that final horizontal velocity will increase, and another mark for mentioning this. But while mentioning this, it's better if you can state this as well. Okay, if you can state draw these diagrams and clearly explain that, it's better. So this question is also done, right? Then let's go to the next question. Okay, right. Then, 14th question. A student exercises by lifting weights attached to a machine. This machine has a cable. Okay, right. So there is a description, and then they are saying there is a tension T in the cable. Right, there's an angle. The person keeps the cable stationary by applying a force of 1 to 1. Determine the magnitude of the tension T in the cable using a scaled vector diagram. Okay. So here, what the person does is, um, determine the magnitude of the tension using a scaled vector diagram. So here the tension forces are like this, right? Okay. So when you draw a vector diagram or simply a vector triangle in this situation, the important point is it should be joining head with tail. I mean, if this is a vector, this is the tail, this is the head. And in the next one also it should be like this. This is the head, this is the tail, this is the head. See, you have head-tail connections in vectors, right? It cannot be something like this. Now, in this situation, in the diagram which I have drawn in this purple color, you have heads connected, right? So here you have a head, here you have a Sorry, here you have a tail, here you have a head. Head means where it is going, okay? Here you have a tail, here you have a head. So tail to tail connection, that is not possible. Okay, but for now we'll draw like this. And what should happen is like if it is something like this. Now initially this 60 was like this, right? Okay, we can bring it to this point. We can bring it to the head of the first vector. And we can draw it like this. Okay, there's no issue. But we didn't change the direction of the vector, we just changed the position of the vector. And in vector diagrams, you can change the position easily. Right? First, we are going to draw a rough sketch of the vector diagram. Okay, and then to complete, like if you consider the actual scenario, the forces will be something like this. Okay, this is the force applied, which is equal to 121 newtons. Right? So that is the actual scenario. But since we have taken it to here, now what have we done? We have taken this arrow to this point, and we should take this arrow to this point. So if you can use a protractor and get a 60 degrees exactly, and then like you can draw a line and then get 60 degrees exactly, and then draw this line, and then you can like you should get a measurement. Okay, uh, you should get a proper measurement first of all. Mm, no, because like we don't know the actual value of t. We only know the actual value of f. We only know that. So like the final diagram should come like this. I'm drawing a sketch of the diagram. Final diagram should be something like this. Because in a vector diagram, the main theory is heads and tails should be connected. Like tail, tail, head, head cannot be connected. That's the main point. All right. So here, what you can do is, since we don't know the value related to tension, what we can do is we know this F is equal to 121 newtons. We know that F is equal to 121 newtons. And they are asking to draw a scaled vector diagram. So what you can do is you can say 20 newtons is equal to 1 centimeter. Therefore, for 120 newtons, you can get it as 6 centimeters. And what can you do? This is how you should actually draw. Okay, you should actually draw. You should get a 6 centimeter. Just draw 6 centimeter line. Okay, and then we know that this is 30 degrees, right? Because t and t is equal. This is 30, and then get 30 from the protector, and then just draw a line like this. Okay, and then from here also get 30 degrees from the protector and just draw a line like this. And now at this point, yeah, it means we know we should, like we are just constructing a triangle, right? Don't think about tension and those stuff. We are just constructing a simple triangle. Before constructing the triangle, we got a small idea about how the triangle might look like using our vector related theory. Okay, then you can complete the triangle, right? You can mark this f, it will be 6 centimeters, and then you can get this t, and here also there will be another t, right? So when you calculate, so you can calculate the distance. Okay, you will get something like 3.5 centimeters for this. Then you can say t is equal to what? 3.5 multiplied by 20, because 1 centimeter represents 20 newtons, so t will be 70 newtons, somewhere close, right? Okay, so what did we do again to brush up the thing? uh, we just drew a basic diagram, and then we knew that uh, all tails cannot be obviously connected in a vector diagram. Then we arranged the vectors, like we took this vector to this position and this one to this position. Okay, I mean, like in vectors you can take it anywhere, right? You can change the position of vectors, but you cannot change the magnitude and the direction of the vectors. Like if you have a certain vector in the left side of the diagram, you can take it to the right side of the diagram. That's no issue. But you cannot increase the or decrease the length of that vector, and also you cannot change the direction of that vector. Okay. So likewise, we applied that principles, and then we somehow constructed a rough vector triangle, and then we tried to construct it in paper. Okay. First we draw this, and then took these angles, and then do the triangle. So here you get 4 marks. So mainly you get 1 mark for this line, this one. Okay, and then another 1 mark for the direction of the arrows. See, it's very important. For marking the direction of the arrows correctly, you get 1 mark, and then the other 1 mark for the shape of the triangle, and then the other 1 mark for this length. Okay, So you should be very careful, right? So 1 mark for force, 1 mark for direction, 1 mark for triangle shape, and the other mark is for T equals 70 Newton. Right. Then let's go to the next question. A cable is attached to a 150 Newton weight. Each time the person pulls the handle, the weight moves up a vertical distance of 0.25. The weight returns to its original position when the handle is released. Okay, so what happens is now there's a cable attached to a, like, now this is in a gym sort of situation. Okay, so you have this handle sort of thing. Then there's a weight of 150 newtons. So what happens is this person can use the hand. I'm not good at drawing, don't worry, and pull it downwards. So then this will go up. Okay, so it will go up. Okay, so and it will move up a vertical distance of 0.25 meters and returns to its original position when the handle is released. The person exercised by pulling and releasing the handle. They do this 90 times in 120 seconds. The exercise machine displays the average power of the person as 35. Deduce whether the power displayed by the machine is consistent with this data. Okay, so what we can do is in one, find the work done. What is the work done in one pull? Okay, work done is equal to force into distance. Okay, so the person is doing work against the gravity, right? Because 150 Newton is trying to pull the weight downwards, but this person is forcefully pulling it upwards. So that's why it will be a good practice for his muscles. So it is 150 into 0.25, which will be equal to 37.5 joules. So this is the work done by one pull, right? Then we can check, like, as a value within a second how many times is this person pulling this. Okay, right? Or we can check take it like this. Now the person is doing it 90 times. In 90 pulls, what will be the energy? To 90, right? Energy, work done. Work done in 90 pulls is this much. Then work done per second. Work done per second, because 90 pulls means 120 seconds. 120. Okay. So what will be the answer? It will be 28.1. It is also a simple question. So here you can get 1 mark. You get 1 mark for this, 1 mark for this, and 1 mark for this. Right. Okay. So that is also something related to work done. So this 14th question is very important. Like, remember the points which I said when especially when drawing this vector diagram. Okay, then we have 15, 16, 17, and 18th questions. 15th question: a photographer shows a ladder that a person can use to climb into the roof space. Yeah, there's a ladder the person can climb like this. Okay, when not in use, the ladder is stored in the roof space and the opening of the roof space is covered by a board. Okay, board is hinged to the ceiling at one end. Ladder is attached to the board by a rail. Yeah, so like when it is not in use, we can just put the ladder up, right? And just like within this hole, we can hinge it and put it up, and when we want to use it, we can make it down and get the ladder downwards. State what is meant by center of gravity of an object. So that is easy. The definitions you should know. We can say point through which the weight of an object is considered to act. Okay. The weight of the board rail is 50 newtons. The weight acts at a distance 0.45. Total length of the ladder is 2.7. Yeah. So here the total length of the ladder they have said as 2.7 meters, right? And if this is 0.85, like we can mark it as data. So this will be how much? 1.85, right? This part. 1.85 meters to the left, right of the hinge, and 0.85 meters to the left of the hinge. Okay, and then there's a board rail which has 50 newtons and acting 0.45 from the hinge. The weight of the ladder is 54. Assume the ladder is uniform. So they have told that assume the ladder is uniform. So assume the ladder is uniform means if you take the center of gravity of the ladder, it is exactly halfway. Okay, so simply speaking, the center of gravity will be at a point somewhere 1.35 meters. Okay, somewhere here. So if the center of gravity is within 1.35 meters, we can surely say the gap between like 0.85 and 1.35. What is how much gap is there? 0. 0.5 meters, right? Okay, so here you have zero point 0.5 meters, and this is the point where the 54 Newton acts. That is one thing that you should take serious. Okay, right? So here we can, and since there are 5 marks, we can write that as well. Weight of ladder towards the hinge. Then they are asking like if this is a situation, explain why the board and the ladder remain in the position. Okay. So we can calculate first moment of board about the hinge. Okay, that is equal to Fx. That means we are taking the moment by this 50 newtons about the hinge. So it will create a which sort of moment? It will create an anti-clockwise moment, as you can see. As you can see, it will be an anti-clockwise moment. Okay. So that will be equal to 50 into 0.45. So what will be the value? 22.5 Newton meters. Then if you take the clockwise moment, which is caused by the ladder, meters. And then we can say resultant moment is clockwise, right? Moment is equal to, if you subtract these two, you get 4.5 Newton meters in clockwise direction. So that means resultant about the hinge will be in this direction. Okay, but like how can it be in equilibrium? So they have said there's a block here, right? So that block you can see here. So there's a small block. So it is saying that there's a small block which prevents the board from rotating into the roof space. Okay, so there's this board, and about the hinge, like if you take this board about the hinge, what happens? It will get a force acting this way clockwise. But what happens is, since this block is there, this block will prevent it. Okay, so we have found that there's a resultant moment in the clockwise direction. So which means the board will try to rotate towards the roof space, because this is the roof space. This area is the roof space. It will try to rotate towards the roof space since there's a clockwise movement, but this block will prevent it. Okay, so if you show that there's a resultant clockwise moment of 4.5 Newton meters, you will already get 4 marks. 1, 2, 3, 4. And then you can say the block will prevent this resultant moment, and it will maintain the system in equilibrium. So that is the answer. Okay. So if you get a question like this, like if you can't feel like how to start, how to end, like if you're not confident about the way of answering the question, but it's okay. Just you can, I mean, do the calculations, because out of 5 marks, you might at least get 3, 4 marks. Right? If you don't know, it's not the best option is not to write anything. Right? Like best option is not to leave the question without writing anything. The best option is to write what you know. Okay. Right. Then another question. The downward force is required to rotate the board away from the block. This force is applied 0.80 meters from the hinge. So they are saying, so now the thing is, now in this situation, the board has a moment of clockwise 4.5 Newton meters. Okay. So if you want to rotate the board away from the block, that means rotate the board sort of in the anti-clockwise direction. Now this is a clockwise moment. This is a clockwise moment. Then what should happen? If you want to just rotate it in the opposite direction, an anti-clockwise moment, clockwise moment of 4.5 Newton meters should be applied. Okay, therefore we can say this side moment is equal to force into distance. So it should be 4.5, because now in the current situation, this is trying to rotate in this direction. So we need to rotate, make it rotate in the opposite direction. Okay, so that's the situation. Equals, therefore we get F is equal to 5.63. I think it's clear. Okay. So if you find this value, you can easily get the other remaining value as well. Okay. Right. Yeah. Then let's go to the 16th question. In the 16th question, uh, a steel object is held by an electromagnet. The magnetic force prevents the steel object falling. Then they are asking, uh, state 2 reasons why the weight of the object and the force of the electromagnetic are not a Newton's third law pair. Now that is a very important question. Okay. So first of all, let's talk about Newton's third law pairs. If you consider Newton's third law pair, there are some similarities and differences. Similarities, and there are also differences. Okay. So one similarity is magnitude equaling magnitude. Another similarity is same type of force. That is a very important similarity. Same type of force. Another similarity is same line of action. Okay. Differences acts on two objects, two different objects, and opposite in direction. Opposite directions. Okay. So if you consider this force, a steel object is held by an electromagnetic. The magnetic force prevents the steel object from falling. What is the meaning of that? Now, there's a steel object. Okay, there is a magnetic force acting upward, and there's weight acting downwards. So these two will be balanced. But like just being balanced doesn't mean that they are Newton's third law pair. If they want to be a Newton's third law pair, they need to satisfy these similarities and differences. Okay. So they are telling like why these two may not be a Newton's third law pair. So we can say one reason just by looking at this. Now, but like this thing is satisfying certain similarities. For example, this similarity is satisfied by these two forces. This similarity is satisfied by these two forces. Same line of action. And this difference is also satisfied by these two forces. But for them to not be Newton's law, like Newton's third law, yeah, what we can say, different type of forces, different type of forces, and acts on the same object, right? Acts on the same object. It cannot be like that because if it is a Newton's third law, yeah, if there is something called action and reaction, then there should be two people involved, right? Even in normal world, if you do something wrong to a certain person, then you might get the return. So you did wrong to person A, and person A did something wrong to person B. That's how two people are involved, right? Two types of forces. Or you can, it's better if you can say not same type of forces, not same type of force. It's on the same object, no two different object, no two different objects. Okay, so that's the scenario between this. Right. So they have given this as well. How the diagram looks like that. Electromagnet is trying to hold the steel object, and then we should calculate the Young's modulus, right? Okay. Yeah. So calculate the Young's modulus of the steel in the cable. So we can calculate the Young's modulus easily divided by E over L naught. So we can say it is FL naught divided by AE. Um, oh no, they have given the strain directly, right? Yeah, they have given the strain. So this is not the way to go. They have given the strain. So uh, on stretch length. Okay, so we can. Yeah, but this is the way to go for Young's modulus. The thing is this: they have given the stiffness. The stiffness means actually something like spring constant. Okay, so uh, if you want to find the force, we can say F is equal to K times X. Okay, and they have given, like we know that Young's modulus is equal to sigma over rho. Okay, sorry, sigma over epsilon, and this is stress, this is strain, right? And they have given that strain is equal to delta x divided by x, and strain they have given a value, right? Strain is 3 into 10 to the power 4 minus 4. I mean, using this strain we can get this delta x. So that is an important discovery, right? That is an, I mean, that's an important quantity that we have found. Okay, so delta x will be 1.14 into 10 to the power minus 3 meters, and if you have found this we can almost find everything. Okay, we can almost find everything. So for this equation I can say E is equal to stress over strain. Strain they have given directly, so we can say stress, like we should find stress, right? Stress is equal to force divided by area. So first of all, to find force we should find K times delta x divided by area. So K is already 2.8 into 10 to the power 7. Now we have found this delta x, 1.14 into 10 to the power minus 3 divided by what is the area, 5.1 into 10 to the power minus 4. So like that way we can first find the stress. So to find the stress, what we did was we found the extension using the strain equations. So we get the force and simply the stress as 6.26 into 10 to the power 7 pascals. And you can use that 6.26 into divided by strain is already given, right? 3 into 10 to the power minus 4. So it will be something like 2.09. It's better to write to two decimal places, okay? That's good. That's a standard. That's good. I hope it's clear, right? We cannot we are not able to get the answer directly because we needed to calculate the extension. So that's the difference here. Okay. Then the next question, 17th question is related to trust, right? Okay, let's go to this question. The force extension graph is shown when the electromagnetic is switched off. The steel object will fall. Okay, when the electromagnet is switched off, the steel object will fall. A student states that the change in elastic strain energy stored in the cable will be transferred to the gravitational potential energy of the electromagnet. Okay, so this is very important. Now, first of all, what happens? Now the electromagnet is holding this steel stone, right? So when this electromagnet is holding the steel stone, the thing is, it is being stretched. Okay, it is being stretched because it has a higher weight, right? And if we switch off the electromagnet, what happens is the stone will fall down. Right? Now you won't get, like, now let's say earlier there was like 100 Newton acting downwards, and you should balance it by giving 100 newtons for tension. Now what happens is when it falls down, you don't need to give 100 Newton itself. Now you only have the electromagnet. These are just example values which I use for you to understand the concept. So you will need to use like 60 newtons, right? So this tension also decreases. That's a scenario that they are talking about, right? So you should use the force extension graph as part of your discussion. Okay. So here what we can do is, like, they have told us to critically use this graph. So let's think about it like this. Now, before, like, when the total weight of the electromagnet and steel object is this point. Now if you take only the weight of the electromagnet, it will be something somewhere like here, right? Total weight of electromagnet only be something like this, and some, like, the extension will also be somewhat reduced, right? Okay. So if you take the change in elastic strain energy, and another important point is the area under the graph. Okay, if you take this graph, the area under this graph shows the elastic strain energy. That is a theory point, right? Area under force extension graph is equal to elastic strain energy. So that is one important, very important point. So what happens is when you remove the electromagnet, what happens is the graph comes from this point to this point. Okay, so if you consider this as a trapezium, say A B C D E, okay, we can say the change in elastic strain energy, change in elastic strain energy. What is the change in elastic strain energy? Hmm? Change in elastic strain energy will be AB, area of ABCD, right? Because initially the shape elastic energy is this much. Finally, what is elastic energy? This much. Okay, so this is the change. The change. Then, what about the change in gravitational potential energy? Hmm? Change in gravitational potential energy. How can you calculate that? Hmm. So, if you take the change in gravitational potential energy, so like we can say it like this. Now, initially, what was the gravitational potential energy acting? Now, there's a weight difference here, right? There's a weight difference. Okay. So, uh, like if you take the change in gravitational potential energy, it is not depending on the extension. Okay. It is actually not depending on the extension. But the thing is, um, now initially you had 100 newtons and you had 60 newtons. Like upward, it had moved a certain distance as well. Okay. It had moved a certain distance as well. Okay. So, like we got the change in elastic strain energy, and then if you want to get the change in gravitational potential energy of the electromagnet, right? Electromagnet weight is consistent, right? Electromagnet has a certain weight. We don't know that weight, but what happens is when this is released, now it moves this much distance. So this object, this electromagnet moves upwards. Electromagnet moves upwards. Let's say a distance of x. This is x, right? It moves a distance upward, right? And that distance, like the distance moved upward, is denoted by this length, because that is the reduction of the extension. Reduction of the extension means, like initially it was here, now it is here. This is the reduction of the extension. Reduction of the extension is equal to how much, like how much upwards the electromagnetic had moved. Okay, so we can say reduction in extension is equal to how much upwards the electromagnet had moved. That's the whole point. Okay, so then if you want to get the work done, we can multiply. Therefore, work done is equal to mass of the electromagnet multiplied by the reduction of extension. Okay, weight of the electromagnet. Okay, we should get the weight of the electromagnet and we should multiply it by how much it had moved up. So that will give the gravitational potential energy of the electromagnet, change in gravitational potential energy. So if you get the weight of the electromagnet, this is the weight of the electromagnet, this is how much it has moved. So this is that area. Therefore, we can say change in gravitational potential energy. Change in gravitational potential energy is the weight of the electromagnet multiplied by how much upwards it had moved. So that is equal to ABCD. Okay. Student says that the change in elastic strain energy stored in the cable will be transferred to the gravitational potential energy. So it is not fully transferred, right? So that should be the conclusion. So we can say change in elastic strain energy is greater than the change in gravitational potential energy. So we can say therefore only some amount of elastic strain energy is transferred to gravitational potential energy. Okay. What we did was, first of all, like there are only two parts in this question. What is the three parts, right? This is the first part. This is the first part. This is the second part, and this is the third part. That's it. For the first part, what we do is we do this trapezium as the area change, because it is defined that area under the force extension graph is equal to elastic strain energy, so we can directly take it. And the second point is taking the change in gravitational potential energy of the electromagnet. So for that, what we can do is we can get the total weight of the electromagnet and multiply it by how much it had moved upwards. And then we can come to the conclusion that elastic strain energy might have been converted to gravitational potential energy, but like it is not fully converted. Right? And actually, in practical scenarios, that is the case, because if you take elastic strain energy, it will be sometimes it will be not fully converted to GPE. Like a certain percentage will be converted into heat, sound, likewise. Right. Then let's go to the 17th question. State what is meant by upthrust. So what is upthrust? Upward force caused by the displacement of fluid. Okay. That's a simple definition. When the balloon is released, the initial upward acceleration is 4.8, so that the weight of the balloon and equipment is 30. Okay. So its upward acceleration is 4.8. So we should show the weight. So is the balloon fully underwater? Oh no, it's in the atmosphere, right? Okay. So what happens is we should first analyze the forces acting here. There will be upthrust and there will be weight. Okay, so we can calculate the resultant force first. Resultant force upward will be equal to mass into A. So let's say it is RF. RF is equal to mass means what? Density into volume. Density into volume of the balloon multiplied by 4.8. So we know the density is 1.23 because the balloon is filled with air and volume is 1.63. So we can get the resultant force is equal to um, no, first of all we should find the weight only, right? We can directly, yeah, we should get it like this, right? Because they have given the volume of the balloon and equipment, but they have given the density only of air. So we cannot just multiply the volume by density and get the weight of the balloon and equipment. So we can get the resultant force first of all. So if you get volume of the balloon and equipment this much, yeah, density of air to down to this much, so we can calculate actually the mass of air here. Because if you take the balloon, the thing is this. Now in the balloon, you are given the volume and you are given the density of air. So the mass of the balloon will be equal to rho v. There's no doubt in that. Mass of the balloon will be directly equal to rho v. Okay. But rather than taking it like that, we can do something like this. Okay. What we can do is, first of all, we can calculate the upthrust. Okay, we can calculate the upthrust. Upthrust is equal to V rho G. So 1.63 into 1.23 into 9.81. So what will be the value of upthrust? It will be 19.67 newtons. Okay, 19.67. And then we can say um, like F equals ma upwards. Okay, so we can say upthrust minus weight is equal to ma. Okay, and we know the acceleration as well. But since we don't know this mass, we can say u minus mg is equal to ma. 19.67 minus m into 9.81. Now my target is to find this mass first of all. I mean the mass of the balloon and the equipment together. Mass into 4.8. So if you simplify this, we can get it here, and we can get m is equal to 1.346 kilograms. Then we can say weight is equal to 1.346 into 9.81, which is equal to 13.20 meters. So I think you understood that. Simply, we get the upthrust. So, and using the resultant force equals ma, F equals ma equation, we can calculate the mass first of all, and then using that mass, we can calculate the weight. Okay, right. So about 13 means it's like close to 13. You might get the answer very close to 13 as well. The graph shows how the density of air decreases with height above the ground. So when you go up, what happens? The density will decrease little by little. Scientists want to make measurements at a height of 25 kilometers where the balloon would stop rising. The balloon will expand as it rises and will burst if the volume exceeds 50. Did you say that the balloon could support the equipment at a height of 25 kilometers without bursting? So if you get 25 kilometers point, what is the density of air? It is this is point 0.2, so it will be this is point 0.1, 0.08, 0.06, 0.04, right? So density will be kilogram per meter. Okay, so um, we can calculate the like the upthrust needed to support this equipment, right? Did you say that the balloon could support the equipment? So what is the mass of the equipment? So we found that the mass of the equipment is 13.2 newtons. Okay. Equipment plus the air, right? I mean, this mass means what we got as 13.2 means the total mass of the balloon and the equipment, right? Total mass of the balloon and the equipment. Right? Even though you go up, it won't change. I mean, even though you go upwards, the mass won't change. Mass will not change surely. So even at this 25 kilometer point, you should support a mass of or simply support a weight of total weight of 13.2 newtons. You should be able to support this total weight. So let's check the upthrust which is required to support this total weight. It is equal to um, V rho G. Okay. I mean, I'm going to check what is the volume needed to support this total weight. Because V into V know the density is 0.04 into 9.8. So here we get the volume is equal to um, something close to 27. Okay. That means if we are 25 kilometers high, the air's density is very low. Okay. Therefore, in order to create a upthrust which is equal to 13.2 newtons, you need to have a volume of 27 cubic meters. And the scientists have found that it will burst only if its volume exceeds 50. We can say 27 is less than 50. Therefore, it won't burst. That's our conclusion. Don't burst. Okay. So you get 1 mark for doing this, 1 mark for this equation, 1 mark for this, and 1 mark for this. Okay. That's a simple observation. And here also you get 3 marks for first for the upthrust, then for the applying this, and then for the answer. This answer. Okay. Right. So you can revise these questions. Okay. Then let's go to the C part. So in C part, they are questioned whether balloon made of a strong material will rise and eventually stop expanding. It will continue to rise until it reaches a maximum height. Explain how and why the velocity of the balloon changes from the release until it okay rise and eventually stop expanding. It will continue to rise until it reaches a maximum height. Explain why the velocity of the balloon changes. That's what they are asking. Okay. So the thing is this: if you take the balloon, first of all, okay, there is a very large amount of upthrust and there is a certain amount of weight. Therefore, since upthrust is greater than weight, what happens is it will get a certain acceleration. Okay, to get a certain acceleration, and this weather balloon is made of a material that will stop expanding. Okay, Stop expanding means like simply the volume won't increase further, right? Volume won't increase further. Then what happens is, now suppose this upthrust is 20, this is 10. Just suppose it's like that. uh, then what happens is, yeah, let's say the balloon reaches its maximum volume. The balloon reaches its maximum volume, and after reaching this maximum volume, it will stop expanding. Okay, it will stop expanding, and what happens is, now if it rises further, like initially the balloon rises up, there is a certain upthrust which is greater than its weight. Okay, and then since then it keeps on going up, right? It keeps going up. Okay, and the other thing which happens is, the in this situation, the density of the air decreases. But the volume will increase, and it will try to maintain the upthrust a consistent value. Okay, so let's think about it like this. I'll take it like this. First, suppose the balloon is here. Okay, then upthrust is 20, weight is 10. Okay, and suppose the balloon is here, still the upthrust is 20, weight is 10. Downward, no issue. Okay, and when it reaches at a certain point, it will stop expanding. That means it will reach a maximum volume point. Okay, now again still upthrust 20, weight is 10. Okay, it will reach this maximum volume point. Maximum volume. Okay, now when it rises from the bottom point to here, what happens is, simply what happened is, the density keeps on decreasing and volume keeps on increase. And what happens is upthrust will be maintained constant. I mean, simply the upthrust won't decrease in this situation, in the early situation, in this region actually. And after this region, what happens is upthrust will decrease. Let's say upthrust becomes 14 newtons, for example. It becomes 10 newtons. Because what happens here is, now U is equal to V rho G. The density of air will keep on decreasing, because that is a universal thing stated in this graph as well. Density will keep on decreasing, but volume will remain constant. Volume will remain constant. Okay. So what happens is, now there is no control for upthrust to maintain its value as a constant. This is the initial situation. Now to make it much clearer, let's say this is 0 meters, this is 10 meters, this is 20 meters, and this is 30 meters. Okay. Then upthrust keep on decreasing, and at one moment what happens is, upthrust equal 10 and weight equal 10, and what will happen? Uh, this will be the maximum height it reaches, right? Upthrust equal 10, weight equals, no. Suppose this is a certain point, but the thing is, it will, now at this point it has gained a certain velocity. Let's say it is 40 meters per second. It has gained a certain velocity. The balloon is rising. Like after passing the 20 meters region, what happens is, after passing the 20 meters region, the upthrust keeps on decreasing. Therefore, the balloon sort of decelerate. Okay, but it's still moving upward. Okay, still moving upward, and then after this point, what happens is upthrust will decrease further. This becomes 6 newton. This becomes 10 newton. Okay, right. Now what happens? This velocity will decrease. This velocity will become like 30. And at one point, it will reach rest. It's like throwing an object, right? Rest. Okay. So that is a scenario, right? From the bottom point to the uh, highest point, weight will remain the same. But what will happen to upthrust? Upthrust will remain the same until the balloon reaches its maximum volume. Okay. Until the balloon reaches this point, eventually stop expanding point, upthrust will keep upthrust will be same, because uh, when the density decreases, volume will increase, and it will try to manage it. But after we pass that point, After we pass that point, after the maximum volume point is passed, there is no control for upthrust to maintain the volume. Therefore upthrust will decrease, and therefore upthrust will keep on decreasing until it becomes zero, right? Zero or a very low value, it will keep on decreasing, right? And while it is keep on decreasing, at one moment it will go below, even below the weight value. See, at one moment it will go even below the weight value. Therefore a total downward force will be acting in the system. Therefore it will come to rest at one point. So that's the scenario. Okay. So what you should say is, first we can say upthrust is greater than weight. Okay. Resultant force is upward. Therefore it moves upwards, right? Therefore balloon accelerates upwards. Then at one point, when maximum volume reach, upthrust starts to decrease due to decrement in, because density of air density of the surrounding air decreases, so the upthrust will also decrease. Then at one moment what happens? At one moment upthrust becomes lower than weight. Lower than weight. Then there will be an overall downward force acting. Overall downward resultant will take the object to rest. So these are the 6 marks you can get. 6 marks. Okay. So it's a very good question. So try to understand this. I have explained this clearly. Like if you can't understand, you can just like watch it again. Okay. Watch this part again. Right. Then let's go to the 18th question. It said that student carried out an experiment using data logger to record the motion of a ball bearing as it fell through the liquid. State the conditions under which Stokes law. You will know Stokes law, so it is applied for spherical objects. Conditions. These are the conditions, and laminar flow. Laminar flow should be there in the fluid. Okay. It should be a small object, and there should be a laminar flow as well. Okay. The graph obtained by the student is below. Explain the shape of the graph. So what happens is when it is the ball bearing is falling through the liquid, what happens is it's first of all its displacement decreases. Okay, its displacement decreases with time. So initially the velocity is zero, we can say. Okay? Initial velocity equals zero because gradient equals zero. Because gradient equals zero, the initial velocity is zero. Okay, so uh, this is also considered downwards. Okay, then what happens? Velocity increases. See, velocity increases. Initially it was zero, it curved a little bit. Okay, velocity increases because of gradient, negative gradient increasing. Why this thing happened? Because there's a downward acceleration. Okay, that's the reason. Downward acceleration. There's a downward acceleration. That is why this increment happens. Negative gradient increase means velocity increases a little bit. It starts at zero. First of all, it's kept at rest due to this weight. It increases a little bit. Then there's weight and there's a viscous force here. Okay, and then what happens? As velocity increases, viscous force increases. As velocity increases, viscous force increases. At one point, both become same and reach equilibrium. So that's the whole point. Okay, so out of these 4 points, you will get 3 points. If you have written 3 points in a clear, meaningful order, you will get the marks. The ball bearing had a diameter. This difference between upthrust on the ball bearing and the weight of the ball bearing is this much. Calculate the viscosity. Okay, so we can use radius is equal to 0.8 millimeters. So we can use calculate this gradient. You can use the graph and calculate this gradient properly and get the velocity. Okay, simply gradient is equal to you get a value like 20.9. Okay, you can calculate and check. Okay, you should do proper calculations. You can simply, which points are better. You can take this point and you can take this point. Okay, you know how to calculate the gradient, right? What we can do is we can mark 2 points, x1 y1 x2 y2, and the gradient will be y2 minus y1 over x2 minus x1. And if you calculate it properly, you will get a negative value, because in this graph it is mentioned downwards, but you can get the magnitude of that value of gradient which you calculate. Okay, so we can say f is equal to 6 by eta rv. So here f means actually the viscous force. Okay, difference between the upthrust on the ball bearing and the weight of the ball bearing is 1.45. So you can directly put that because they have given the force. Okay, so what here the meaning of this thing is, now if there's the ball bearing like it's falling downwards, this is the weight. There are two forces acting upward, one is upthrust and one is the viscous force. Okay, so here if we apply f equals ma, okay, no, it's not f equals ma, like at this point we assume constant velocity. That means we can say Fv plus u is equal to W and Fe is equal to W minus u. So what have they given as data? Difference between upthrust and weight means actually the viscous force. They have given the viscous force indirectly. Okay. So we can substitute the values to 1.45 to 10 to the power minus 4 is equal to 6 pi into eta into zero point 0.8 into 10 to the power minus 4 into 20.9. So is it, what are the units? This is centimeters per second. So since it is centimeters per second, this is centimeters per second. So you need to convert it into meters per second. So you need to multiply by 10 to the power minus 2. Okay, so that is important. You need to multiply it by 10 to the power minus 2 in order to convert centimeters per second to meters per second. Then you will get the answer for viscosity as 0.046. The student heated the liquid and repeated the experiment. Ball bearing took less time to fall. Explain why. So if temperature is high, we can say if temperature is high, viscosity is high. Viscosity is low. Okay, so viscosity low means you can say like if you take it mathematically, we have a certain weight, we have a certain thrust. Like simply the you can say resultant down upward force is low, and it means downward force is high. Resultant downward force is high. Okay, right? Therefore we can say takes less time to fall. That's true, right? Because like there are two situations. In one situation, you have a higher force downwards, and in the other situation you have a lower force downwards. So if you have a higher force in the downward direction, it will take less time to fall. So you get 4 marks for these points. Right. So this is the full discussion of this question paper. And like if you have any questions like or doubts, you can just like if it is difficult to solve them in the comment section, you can just drop a message to this number, okay, through WhatsApp. Related to this discussion, if there are any doubts, you can send it. Okay. And I'll be there'll be some other paper discussion videos in the channel as well. You can check them as well. If they're not still uploaded, I'll upload them. Okay, so that's it.